Today's goal is to use trig functions to model x and y values with respect to time. This is similar to an objective called parameterizing that you might see in future math classes. Okay, let's take a look at our examples. In an amusement park, there's a small Ferris wheel called a kiddie wheel for toddlers. We'll use the points in the circle at the diagram on the right to represent the position of the cars on the wheels. Kiddie wheel has 4 cars, making 1 revolution each minute, and has a diameter of 20 feet. Oh, that makes sense if the radius is 10. Okay. Assume t equals 0 corresponds to a time when car 1 is closest to the ground. Sketch the height function for car 1 with respect to time. With respect to, of course, means that our x variable is t, as the Ferris rotates for 2 minutes. Okay, so let's figure out what's going on here. Sketch the height function. Well, where is the height at t equals 0? T equals 0 means our car is here, and I can tell from the diagram that the car is 5 feet above the ground. So let's plot that value here. Okay, I'm assuming the cars go from direction 1 to direction 2, so let's assume we go here. If we make 1 revolution every 1 minute, it'll go all the way around the circle. So at t equals 0 and t equals 1 minute, we'll be back here. And we want to go for a total of 2 minutes, so we'll be back here again after 1 minute because that's 1 full revolution, which means that we will be here at 1/4 of a minute. So t equals 0.25 seconds. We'll be here. And if the radius is 10, plus we're that additional 5 feet off the ground, that means we're at 15 feet off the ground. 1/4 of a second later. This would be the number of seconds after the Ferris wheel starts spinning. Well, that makes sense because we wanted to write an equation of a function with t time as our x value, and then this would be the height off the ground in feet. Okay, so let's keep spinning. We keep spinning, we go, 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 we land here. If it takes us a full minute to get around, it'll take us half a minute to get halfway around. So that would be, let's see, this would be 10 feet off the ground. This is another 10 feet off the ground. This is another 5 feet. So 10 plus 10 plus 5, that would put us 25 feet above the ground, half a second later. Then we move here. This is 10 plus 5. This would be 15 feet off the ground, 3/4 of a minute later. Sorry, these are minutes. Okay, and then we spin back here. So then we're only at that 5 feet off the ground, 1 full minute after we start. And then this just keeps going. So another 1 1/4 minutes. We're back up here at this position, 15 feet off the ground, at 1.5 minutes. We're at the very top of the Ferris wheel, 25 feet off the ground, at 1 3/4 minutes. We're back in the middle, and at 2 minutes, we're back at the edge, only 5 feet off the ground. Okay, so sketch the height function. Let's just go ahead and connect these dots. I can tell that the values are going up and down in a circular fashion, right? You're traveling around a Ferris wheel, so you're traveling in a circle. So I'm going to connect these with a nice circular curve. Okay, find the formula for a function that models the height of car 1 with respect to time as the kiddie wheel rotates. So we already made a sketch of the function, so we're just writing a formula for the sketch. So let's take apart, what do we notice about this sketch? Well, I notice that it has an amplitude of 10 feet. I notice that it has a period of 1 minute. And I notice, we're running out of colors here. I notice that this looks like a cosine function. Right, cosine would look like this. It would start at a max. It looks like a cosine function that's been reflected. So my function would be this. F of x equals, it'll have the form a times cosine of bx plus k. But it's been reflected, so we'll say f of x equals negative. A is the amplitude, so negative 10 times the cosine of b is 2 pi divided by the period. So 2 pi divided by 1 minute in this case. So 2 pi x plus k is my midline. Forgot to sketch that in. And my midline is at y equals 15 feet. So plus 15. Okay. Let's take a look at the next. This is actually our last example of the day because it's pretty dense. So hang in there. Malik wants to drive a go-kart around an outdoor rec center, but his mom is worried because he's terribly allergic to bees. They finally agree that Malik can complete 3 laps around the track, as long as his mom stands next to the track with an EpiPen in case he should be stung while he's driving. Malik starts driving directly south of the center of the circular track. So he's right south of the center. He's going around a circular track. Let's try to start putting this together. Let's see. Here's a very messy picture of the track. This is going to erase the whole thing, I think. Here would be the center of the track. It says he starts driving directly south, so that would put him here. Okay, if it takes him 4 minutes to make a complete lap, I'm sure we'll come back to that, around the track, his mom stands 6 feet east of the easternmost point of the track. Well, the easternmost point would be this here, and she's standing an additional 6 feet here. So here's mom, and here's Malik. Write equations x of t and y of t that represent the horizontal and vertical distance Malik is from his mother t minutes after he starts driving her go-kart. It should say driving his go-kart. Sorry about that. Okay, so he's driving around the track. He's driving south of the circular track. Okay, well, it should have said in here whether or not he's going clockwise or counterclockwise, so I do apologize for that typo. Let's assume in this case that he's going clockwise, so let's add that. If he drives clockwise around the track. Okay, if he's driving clockwise around the track, this is similar to the Ferris wheel problem in that it might help us to look at like stopping points. Like, when is he going to make it to this point? When is he going to make it to this point? Okay, so he's starting, and we want to talk about the horizontal and vertical distance away. So let's just pick one to start with. Let's start with vertical distance. This means ignore the fact that he's obviously west of his mom, but how far is he north or south of his mom, right? So if we're ignoring the fact that you'd have to drive west to get to him, how far would mom have to run south if he had an allergic reaction? Well, we need information about the track. The circular track has radius 25 feet. So he's starting here. It says mom is directly east of the track, so we should assume that he is 25 feet south or below his mom in that sense. Okay, so let's start drawing a diagram. At t equals 0, he's 25 feet south. We'll use north or south as positive and negative values below his mom. Okay, so then if he's traveling clockwise around the track, he's going here, he's going here, he's going here. The next place another point of interest would be this point right here. It tells us it takes him 4 minutes to make it around the track. So if he's gone a fourth of the distance, this is at t equals 1. He's here. How far is he south of his mom? No feet south of his mom, right? If he were to have an issue, she would run straight west to get to him. So this would be 1 minute later. Next, he travels here. If it takes him 4 minutes to get all the way around, he's halfway there. So this is at 2 minutes, and I can see that he's 25 feet above where his mom is standing. So we'll put that here. And then he travels. At this point, he's standing directly west of mom. He's 0 feet above or below mom. So this is 1 full lap, so that would be 4 minutes. Oh, I'm sorry, not yet a full lap. This point here, once he makes it back to the start, this would be a full 4 minutes. And so that's why we'll say at 4 minutes, he's now, again, 25 feet south of mom. So this is going to continue, right? He's going to drive around the circle and continue to go around the track. It says he can make 3 laps around the track, so let's make this happen 3 times. We'll extend our graph a little bit. He's going to go in this same pattern one more time until he stops where he landed. So let's go ahead and sketch this function in. Our ultimate goal is to write the equation of the function. I think it's way easier to write the equation of the function when you have a chance to sort of sort out the pieces of information, maybe by drawing a picture. Okay, so when we draw this picture, we can see clearly that the amplitude is 25 feet. We can see that the midline is at y equals 0. We can see that this looks like a cosine function, except that it's been reflected. So his vertical distance, what they say they wanted us to call it, y of t. His vertical distance, y of t, would be negative 25 cosine of, if the period is 4 minutes, that coefficient b will be pi over 2 t plus 0. So you can just write it as y of t equals negative 25 cosine of pi over 2 t. Okay, that's his vertical distance from mom. Now we need one more thing, which is write the equation of his horizontal distance from mom, and we're going to call that x of t. Okay, so we've got this same diagram. We can come back to it and add on to it if you wish. Let's see, we're running out of colors here. Okay, he's starting in the same place, but when he starts, he is 25 feet, the radius of the track, plus an additional 6 feet to the left of mom. And so this would be 31 feet west of mom, or left. And then he travels around the track at t equals 1 second, 1 minute. He's here. At this point, he is 25 feet plus another 25 feet plus that 6 feet. So that would be 56 feet left or west of mom. Then he travels up here. This puts him at another 25 plus 6, so this would be 31 feet left of mom. And then he moves here, which is only 6 feet left of mom. So in the span of 4 minutes, he started 31 feet, then 56, then 31, then 6. So let's draw a sketch of this. This is my time, and this is x of t. He was first 31 feet to her left, so that's a negative value. Then he was then he went further to her left. He went 56 feet to her left, then back to that 31 feet, and then at this point, this is a little bit out of scale. At his highest point, he was still 6 feet away from her. And then the cycle repeats. Oops. I am so sorry. Oh, there we go. Okay, so then the cycle repeats. He gets further away from her horizontally, then closer, and then this repeats 3 more times. But if we wanted to draw a sketch of the situation, we would want to make sure that we showed 3 full periods, because he's going around the track 3 full times. But our goal isn't to make a sketch. Our ultimate goal is just to write an equation. So you can stop with the pattern as soon as you see the pattern, enough information to write an equation. So in this case, our amplitude would be 25 feet. That makes sense because that's the radius of the track. This time our midline is at y equals negative 31. We can see that this looks like a sine function, except that it's been reflected, since it's going towards a minimum before it goes towards a maximum. So this is the function x of t. A little weird to have x be your dependent variable, right? X is acting as y this time. X is equal to negative, since it's been reflected across the x-axis, negative 25 times the sine of, my period is still 4, and so b would still be 2 pi over 4, which is pi over 2. So x of t equals negative 25 times the sine of pi over 2 t minus 31.